Okay, so now in this lecture we will discuss about some basics of the structure level modeling with few examples. Already we discussed these points in structure level modeling. In this level of abstraction, we explains how the system is implemented rather than the functionality. So we concentrate on the implementation part of the system. What are the various gates which are used for the implementation, how they are interconnected. So we never bother about the functionality of the system, right? We bother about the implementation part. In structure level, we explain the system in terms of the interconnection of gates, right? So just now I said same thing. Verilog has few predefined logic gates which can be instantiated in a module to create a structure design. So there are some predefined logic gates in Verilog, and those logic gates can be used for writing the Verilog code at the structure level. So these are the predefined gates. We already discussed few of the gates in earlier lecture, but few more gates I have included here, and those are basically tri-state gates. So now here this first one, and this is the predefined AND gate, right? It has one output and the number of inputs will be more than, means 2 or more than 2. So, and NAND gate, this is also predefined, OR gate, NOR gate, XOR gate, XNOR gate, right? So all these gates up to XNOR, they have multiple inputs and single output. Now NOR gate, it has single input and single output. Buffer, BUF, is for buffer. So this is the buffer, right? This is buffer. Here we have input and here we have output. So this is BUF. Right? So whatever is the input logic, same logic you will get at the output. Then another is now remaining 4. These are tri-state, right? These are tri-state. So first one we will see this one. It is not if 0, right? So it is not if 0. So it is like this. It is like a NOT gate having one input and one output, and apart from these there is another control input, right? There is another control input. We call it as CTRL, control input. So so this is not if 0, means if this control input, if this is 0, right, then it acts as a NOT gate. Then it acts as a NOT gate. and if this control is 1, then the output will be in high impedance state, right? So output section is disconnected with the input section if the control signal is 1. So this is not if 0. Same way there is not if 1, right? So in not if 1, I write here, in case of not if 1. So here if the control input is 1, then it acts as a NOT gate. Then it acts as a NOT gate, right? And if control input is 0, then high impedance state, right? So this is about not if 1. And there is another tri-state gate, that is buffer if 0. So here we have seen the buffer, and buffer if 0 means here the control input, right? This control input. So here if control is equal to 0, right? We are talking about buffer if 0. Okay, control is 0, then it acts as a buffer, right? Whatever is at the input, it will be transferred to the output. And if control is 1, then output will be in high impedance state. And another is buffer if 1. So in that case, if the control input is 1, then it acts as a buffer, otherwise high impedance state. So these are predefined gates, right? And in the predefined gates, when we use these gates for instantiation, then first we have to write this keyword and inside the bracket first we have to mention the output. After that only we have to mention the inputs, right? So this sequence we have to follow. First we have to write outputs, then we have to write inputs. Okay. Now there are some constraints, some restrictions when we are instantiating gates. The output port must be connected to a net, right? So example, wire is one of the class of the net, right? One of the category of the net type. So here these outputs, so whatever output you are mentioning in your instantiation, these outputs must be net type. Okay, these must be net type. Another restriction, the output port is a wire by default. By default, the output port is a wire unless explicitly declared as a register, right? So by default, when we are declaring input port or output port, at that time, if we are not mentioning anything, then by default it is a wire, means net. If we want to declare it as a register type, then we separately we have to declare, otherwise by default it will be wire. The input ports may be connected to nets or register type variables. So here this means the inputs, right? Suppose this is some AND gate, right, having 2 or 3 inputs. This is the output. So output must be connected to net type, and these inputs, they can be net type or they can be a register type, right? They can be a net type or register type. So this is one restriction. Another is they have single output and can have multiple inputs except NOT and buffer, right? So except NOT gate and buffer, all the gates have multiple inputs. So here you see inputs. It is not mentioned how many inputs. At the time of instantiation, how many number of inputs we allocate to this gate, it will become that many number of AND gate, that many input AND gate, right? It depends upon the designer. At the time of instantiation, he will decide, he will assign the number of inputs. Another constraint, Verilog has few predefined logic gates which can be instantiated in module to create structure design. So predefined logic gates are there. We can use these gates for the instantiation purpose. When instantiating a gate, we can give an optional delay. We can give the delay also when we are instantiating a gate in our module, but this delay is used for the simulation, right? Suppose somewhere we have used this gate, AND gate, right? And we have mentioned some input and output here, and if we mention this type some delay like 5 unit delay, 5 microsecond or 5 microsecond, 5 nanosecond. So this type of delay you can mention, right? But this delay will be used only during the simulation, right? But at the time of synthesis, after the synthesis, at the time of synthesis, this delay will be ignored by the tool. Okay, this tool will not recognize this delay. It will simply implement the circuit, and after the implementation, what is the real delay? That delay you can see, right? And up to the simulation, you can mention some delay of the gate. That see, suppose this is my 1-2 input AND gate is here. So here I can mention some delay that this gate is having a delay of 5 unit. Okay, that type of delay you can mention, but this delay is used only for the simulation purpose. During the synthesis, the tool will ignore this delay. Another is optional label can be used with instantiated gate. So you can mention the label. Label means you can, this is a AND gate, right? Now suppose in a circuit there are another and 2 input AND gate is also there, right? There is another 2 input AND gate. So now both are predefined AND gate, both are AND gates, 2 input AND gates. So to differentiate these two gates, you can give the label, like this is my A1, gate number A1, this is my gate number A2. Like this you can give the label, but this is optional. If you want, you can give. Okay, see here the example I have given, and #5. So this #5 is the delay, right? Then G1 is the label. So I have given the name to this. This is AND gate, and I have given one label to it as a G1. So this is label. And this label is optional, right? If you don't want, then you don't write. And within bracket, whatever you will write first, it will become the output port, right? Since all the gates have single output, so the first identifier will be the output and remaining will be the inputs, right? Remaining will be your inputs. Okay, so here one Verilog code of half adder structure module is shown here. So this is one half adder. So here we have one 2 input XOR gate, and X1 is the label of this XOR gate, right? Suppose I have given the label X1. This is the 2 input AND gate, its label I have given X1. So XOR gate is connected to my input port A and input port B. Same way the AND gate is also connected to input port A, input port B. The output of XOR gate is connected to S port, that is sum port, and uh, the output of AND gate is connected to another output port, and its name I have given C, which indicates carry out. So this is a code module. Then I have given the identifier. I have given the name of this module as half_adder. Then within bracket I have mentioned my input and output ports A, B, S, C. Then terminate this statement by semicolon. After this, to declare which one is my input port, I have used the keyword input A, B. Terminate this line by semicolon. Then I will declare the output port output by using keyword output S, C. So S and C, which are my sum and carry, these are my output ports, and again I terminate this line by semicolon. Now I am doing the instantiation. For the instantiation purpose, I will use the predefined logic gate here. So I am using my logic gate XOR. This is predefined gate, and this X1 is the label of this XOR gate. In this particular example, only one XOR gate is there. So if you want, you don't use this X1, but there may be the cases. Suppose in any circuit there are 5 2-input XOR gates. So there it is useful for you to give the labels of these 5 XOR gates, right? But here it is not required. Even then, if you are mentioning, then also no problem. So I have given the label of this XOR gate as X1. Then instantiation I am doing. First I will write the output port of this XOR gate. So the output port is S. So I have written here S. After this, input port of this XOR gate. So it is A and B. So S, A, B, and terminate this line by semicolon. So instantiation of XOR predefined logic gate is completed, right? So here what I am doing with the instantiation, I am connecting the input and output ports of this XOR gate with the input and output ports of this module, right? Now another gate I am instantiating here, that is the AND gate. I have given the label A1, and how it is connected with outside world, with output C and with the input A and B, and I have terminated this line by semicolon and module. So this is the complete code of half adder structure model, right? Okay, now I will just show you the demonstration of this this particular program in the software. Okay, I will just copy this code. Then I will run this software. Already in previous lectures, I have shown how to use this software. Okay, simply what I will do, I will paste my code here. Okay, this code is pasted. Now what I will do, I will do the simulation. For that, first I will check the behavioral check syntax. I will check whether syntax is correct or not. So now you can see here in this console, message is displayed. Process behavioral check syntax completed successfully. So there is no error in the code. Now I will see here, I will simulate the behavioral model. I will do the simulation now. I will apply clock signals to the input A and B, and according to this code, the output sum and carry will be generated. So to A, I will apply one clock signal, right? I will give the clock signal of time period 10 microsecond with 50% duty cycle. One clock I have assigned. To input B, I am assigning another clock of 14 microsecond time period with 50% duty cycle. Okay. Right. Now I will run this simulation for 100 microsecond. Okay. Now we will see. So here you check. Right now this vertical line, yellow color, whatever. So at this particular time, during this time of the simulation, this time of the simulation is, see here it is written 2.85 microsecond. At simulation started at 0 microsecond. At 2.85 microsecond, what are the various values of input A and B? So you see here, the value is A is 1 and B is 1. So in this case, what should be the output? So you see sum is 0 and carry is 1. So this is the required functionality. When A and B are 1 and 1, then sum should be 0, carry should be 1. Now I will check here. The input conditions are input A is 0. See, first one is input A, second wave is input B, third wave is for sum, and fourth wave is for carry here. So now at this 6.9 microsecond simulation time, input A is 0, B is 1. So for this condition, sum is 1 and carry is 0. Okay, this is also correct. Now here I will check at this time 9.55 microsecond. At this time A is 0, B is 0. So due to this, my sum is 0 and carry is also 0. Now I will check this condition. A is 1, B is 0. So sum is 1 and carry is 0. So now this waveform shows that the functionality, whatever code I have written, that is giving me the functionality of half adder. Now I will synthesize this. For that I have selected this implement option and I will do the synthesize. I will click the synthesize tool. So this synthesis is used to generate the netlist, right? So netlist will be generated. There are two forms of netlist you can see. One is RTL, register transfer logic, and another is technology schematic. In technology schematic, you will find your design, how it is implemented in LUT, lookup table. Because basically FPGA we are using for the implementation. That's why in technology schematic, you will find the lookup table for the implementation of your design. First, I will show you RTL schematic. Yeah, this is the module. See two inputs A and B. No, this is for AND gate. Okay, whatever This is for AND. I have to show you 1 minute. Okay, we'll see. And here it is showing. Right. 1 minute. Because previously I have written the AND gate code, so it is showing that. 1 minute. So select this. Half header. Okay, now half header. So technology schematic. It is showing the technology schematic by using lookup table. How it is implemented. See here. This is half header having ports A and B, C and S. You double click this. Now you see. So here the logic is implemented in two LUTs. This is one LUT, right? And this is another LUT. These two LUTs. It is written here LUT, right? Inputs are B, A, C, S, right? So here if you double click this LUT, what is the logic? It is showing here AND logic. AND logic is implemented. AND logic is implemented in this LUT. Okay, that's why you see here you will find the carry. This LUT, this carry is generated through this LUT, and sum is generated from this LUT. So in this LUT, two input XOR logic is implemented. You can see this is two input XOR logic. This is the equation truth table K-map. So you see this two input XOR logic. This is implemented in this LUT, right? So this is the technology schematic. And if you want to see the RTL schematic, then you can see this RTL. 1 minute. So RTL, what I will do, I will run this. I will open new source file. Right there, we can get Verilog module. HA half header, A, B, S, C. S and C are the outputs. Okay. Next. So here HA, right? HA is the name of the module. I have given HA. No problem. This HA. Okay. Okay, here some problem is coming in this. Well, I will do one thing. I will create a new project, right? I will create a new project. Okay. Now I will try to run this. I will open new project now, and because technology schematic is showing the result, but in RTL it is not showing, so I will check why it is happening like this. A new project. HA. I will give the path to 1. Okay. Right. Okay. Now I will open a new source file. Verilog module. HA. Inputs are A, B, outputs are sum, carry. Okay. I will paste the code here. Right. Now I will synthesize this. Okay, now it has been synthesized. Now I will see the RTL schematic. Now you see in RTL schematic you may find the logic in this way. This is AND gate, and here the XOR logic is implemented in this way, right? So this is RTL schematic. Here it is not showing the technology. How it is implemented in the technology, it is not shown here, right? Okay, so this is about the right. So now we will see another example of structure model of full adder, right? So in this case, this is the full adder. It is having output port S and C, sum and carry. Now here there is one 3 input XOR gate which is connected with input ports A0, B0 and C. And now there are 3 AND gates. First is, I have given here label because there are 3 2 input AND gates. So to identify these gates, I have given the label A1, A2, A3, right? And how they are connected? A1 is connected to A and B. A2 is connected to B and C in, and A3 is connected to A and C in, right? In this way it is connected. Now the output of the AND gate is connected to a 3 input OR gate, right? I have given the label to that 3 input OR gate as O1. So now here you can see there are 3 intermediate wires. This is one wire. This wire is neither connected to input port and nor connected to output port. but it is internally connected between the components. So these type there are three wires, L, M and N. So if any of your design you find these type of intermediate wires, then declare these wires as wire. Okay, always remember, if in any circuit you find any intermediate wire which is not connected directly with your input port or output port, then you have to declare these wires as wires. So you now see this code module. I have given the name to this module as full underscore adder. Then there are five ports, A, B, C in, S, C. Input ports are A, B, C in. Output ports are S, C. Now you see here I have declared wire. So wire is a net type. I have declared three nets. What are the name of these nets? L, M, N. Right? Now I am doing the instantiation and label I have given A1. How my A1 is connected? First you have to write the output. It is connected to output with a wire L. So I have written L. Then you have to write input. So A1 AND gate is connected to inputs A and B. So here I have mentioned L, A, B. First you have to write output, then you have to write input. Then terminate the line by semicolon. Then I will instantiate the second AND gate. So its name is also same AND, but I have given the different label. Right? By label I can identify, and this is another AND gate. So its name is A2, and how it is connected? Output is connected to the wire M, and inputs are connected to B and C in. So see here, M, B, C in. Now you come to third AND gate, and its label is A3. This is A3. How it is interconnected? It is connected with output. Its output is connected with the wire N, and inputs are connected with A and C in. So see here, N, A, C in. So these are the three instantiation of the AND gate. Now I have done the instantiation of OR gate. Now you see the OR gate, how it is connected. First you have to write the output, that is C, and the input. Input is connected to L, M, N, to these three wires. So see here, OR is a predefined OR gate. O1 is the label. Then C, L, M, N. In this way I have done the instantiation. Now you see the instantiation of XOR gate. So see here XOR gate, how it is connected. Output is connected to S, and inputs are connected to A, B and C in. You see here output is S, then inputs are A, B, C in, and the label I have given X1. So this is the full code of full adder, right? So I will take this code and I will just demonstrate this simulation and synthesis. Okay. I will create one folder to okay, I will open new project. I will give the name of this project as FA full adder. I will give the path to my folder number 2. Next, finish. Okay. Now I will open the source file. I will select Verilog module. I will give the name of my module as FA. Next. Inputs are A, B, C in. Outputs are S, C. So I will select the output here because by default it is input, so I have to change it to output. Okay, finish. Now here I will copy the code. So it is FA. Okay, I will save this. Now I will do the simulation first, right? I will check the syntax. So there is no error. Now I will simulate this code. I will give the clock signal to A, B, C, and depending upon the code, sum and carry will be generated. Okay, so to A, I am giving a clock of 10 microseconds time period, and in B, I am giving a clock of 14 microsecond time period, and in C in, I am giving a clock of 17 microsecond time period. Okay. Now I will run this. Now these are the waveforms. So first waveform is A, second is B, third is C in, right? And below this sum and carry. And below sum and carry you can find L, M, N. These three wires, waveform of these wires also shown here. But we will concentrate only A, B, C in, which are the input, and sum and carry, S and C. So here at this time you see A is 1, B is 1, C in is 1. So what should be the sum and carry? So sum and carry will be 1 and 1. We see the next case here. A is 0, B is 1, C in is 1. So now in this case sum is 0 and carry is 1. This is also okay. Now at another condition, A is 0, B is 0, C in is 1. So for this sum is 1 and carry is 0. We see here A, B, C in. All the inputs are 0, so sum and carry are also 0. Check here. A is 1, B is 0, C in is 0. So sum is 1, carry is 1. So from this waveform I can conclude that this Verilog code is giving the functionality of full adder. So now I will implement this by synthesizing this code. Okay, it is synthesized. I will try to open the RTL schematic. Yes, RTL schematic. This. So this is the RTL schematic. Okay, this is the module FA. 3 inputs A, B, C in, and 3 ports A, B, C in is here, and C and S is there. Now, how this is implemented? This logic in this way. So in RTL schematic you will find the logic in terms of gates, right? In terms of gates you will find the logic, and in technology schematic you will find the diagram in terms of lookup tables, right? So here now click this. Now you will find how this logic is implemented. For the implementation, we need two lookup tables here, right? So this is one lookup table and this is second. In this lookup table, this logic is implemented, right? And in this lookup table, this logic is implemented. Okay, this is a truth table, this is a K-map, this is the equation, this is the schematic, this is schematic. So this schematic is implemented in LUT 3_96, right, at this, and at this LUT 3_E8, at this instance, this logic is implemented. So this is a netlist. So in this way, we can run the code and we can see how means the functionality of the design, and synthesis part also we can do. Okay.